question on the floor is page 278, number 15. And this one is a real world problem, believe it or not. Because in the real world, what you want to do is, even if you have like a lemonade stand, or if you're making Dell computers, you want to know how many computers do I have to make and sell just to break even, just to get back the money that I had to pay to do that. And then you say, okay, let's sell more than that, so we make a profit, right? So, but the first point you want to find is that break-even point. When will the cost that I had to put out there, the overhead, the materials, equal the revenue that I bring in? When will that be true? So break-even point is when cost equals revenue. Okay. It's after that point you start to make a profit. So this is a good point to know where it is. Right? So in this case, they tell me, on number 15, they tell me the cost was 85x plus 900. So it was like $900, whatever, rent or water or electricity, whatever, plus $85 per thing that I'm making. That's my cost. And the revenue, I'm going to sell those for $105 a piece, of course, so that eventually I can make a profit. I'm going to sell it for more than it cost me, so I can make that back and then eventually make money, profit, so my company can stay open. How are we doing so far? And this is good. Pretty much as real world as you can get. In the real world, these equations normally are not this nice, but the idea is still the same. You find out where they meet. So the funny thing is, let's see, which section is this? Oh, okay. Find the break-even quantity and decide whether the product should be produced on the blah, blah, blah. So break-even point is when cost equals revenue. So what equation can I set up then? Exactly. Cost equals revenue. So 85x plus 900. I want the amount of money I had to pay out to equal the amount of money that I'm pulling in. And if you think about it, isn't that where this line meets that line? We're really kind of doing substitution. I want C to equal R. So then I put that in place of C. I'm seeing where these two things meet. So if I were to graph these two things, here's my cost. It starts at 900 and it goes up. My revenue starts at 0, right? But it goes up faster. So at some point it's going to catch up with my cost. That's the number of things I have to make just so I can get back the money that I spent to get my business going. Cool. Maybe. You hear this all the time, like when you solar power generators or like solar grids. They say at some point you're going to like earn your money back. It's that break-even point where the money you paid to get it equals the money you saved with it. So after that point, you're saving money. Have you guys ever heard of that kind of thing? That's a selling point for solar cells. Is that at some point, I know it costs a lot of money to put it in a damn house, but like 5 years later, you're just making money after that based on what you would have been paying for electricity, right? So that's a very simple equation to solve now. You just had to know what the idea was to set it up. So how do you solve that equation?
Subtract 85?
Yeah, subtract 85. Get my x's together. And then 5 by 20. 90 divided by 2.
45.
45, cool. So they have to, if they make and sell 45 of these things, whatever it is, I don't know if they were that specific. No. If they make and sell 45 of these things, they will break even. They won't lose money, they won't gain money. They'll just have been able to pay back the money they owe. If they make and sell more than that, what happens? They earn money, they make a profit. Yeah. Okay, so in the real world, that's kind of a moving target because they're changing the prices based on their demand. So to be a financial analyst, you can make a lot of money because you're the guy that's making the company money by analyzing all the freaky equations. The idea, though, is the same. Where does the freaky equation for cost cross the freaky equation for revenue? That's my break-even point. And then we say, make and sell more than that. And they go, okay, we will. Right? And then, there you go. That's the target amount you want to sell so you can make a profit. How we doing? If you're at all interested in business, that's cool. If you're not, it's math, and you got to do that for my class anyway. So there you go. Okay. So any questions on that one? Is that? Yeah. I think part B says decide whether the product should be produced, on whether it will earn a profit, and if I can make more than 45 of them and sell them, that'll earn a profit. So part B sounds like a good thing. If my X was 3 billion, I might say, holy crap, I'm not going to do that.
The answer would be no, yeah. It says no more than 38 units.
Where did it say?
No more than 38 units.
Oh, no more than, oh, there, no more than 38 units? Oh, crap. Well, if I can't make and sell more than 38, then is this a good idea?
No.
No. Okay, thanks. I didn't see that they put a limit. So I can't do 38. I got to make 45 just to be able to break even. I'm not going to do it because I'm guaranteed then to lose money if I can't make as much as I need to just to get my money back. Okay, maybe. All right. Any other questions from?
Number 12 on 277. Yeah, like I got some of the equations from like some other guys here, but for some reason my brain's not working. I'm at a blank.
All right, let's see. Let's start from scratch here. Number 12. Read through that one. It's about the course line and Beauty and the Beast. And that's on page 277.
Yeah, number 12.
You want to read it out loud?
No. Everybody read in unison, please.
Popcorn.
Two other musicals. Huh?
Is it popcorn?
Pop?
Popcorn reading?
No.
It's
What's that?
where we'll be reading and then you read like, your chapter, then you have to pick someone else to.
Oh, is that what they're doing now in high school or whatever?
That was like elementary school.
We've done ever since I was
Yeah.
Let's see, Jeff is 39.
You never popcorn.
Back in my day, I remember reading something in my nutrition class and my voice was cracking, so everybody was loving it. You know, when you're that age, you're like, hey, Jeffrey, no. Apple on the tea. I remember that. I didn't have any popcorn. So what are my two unknowns here? What do I need variable names for?
For the course line. For the course line, Beauty and the Beast.
I love it. So the number of performances. Right, for Beauty and the Beast and course line. So I'm going to call Beauty and the Beast B and course line C. I like it. So now I need to find I have two unknowns, so I have to find two separate equations. As many things I don't know, I need that much information. So the easy one, B plus C must be what?
1159.
11,598. Now here's the one that you got to be careful. There were 676 fewer performances of this than there were of this.
So is it 2x?
B minus C equals 676.
C minus negative 6. B equals C minus 676.
Good. Right, because there were 676 fewer of this than there were of this. So there were more of this one, right? So if you do this minus 676, that's how many there were of Beauty and the Beast. There are a couple different ways to write that, but to me that's the way I think of it first.
Wait, how do you get all the nuances?
Say again? Beauty and the Beast and chorus line. And they told me together there were this many performances. That's an easy equation. And then it said there were 676 fewer performances of this than there were of this. Now the biggest mistake I see is people subtract this from B. But isn't B the smaller number?
Yeah.
So there are 676 fewer performances of this than there were of this. So this minus 676 is B.
Okay.
Because there were less B, so that's the one I got to subtract from C to make it go down to B, right? Now, what process can you use?
Substitution.
I love it. It's set up beautifully for substitution, right? B equals that. So in number 1, I can write B plus C, but instead of B, I write
C minus
676, yeah. Well, I'm not going to put those in. So this is B plus C. So B plus C is 11,598. And now I can solve from there. Not too bad.
So you don't have to write the B in?
I did. B is this. So when I see B, I could, if I wanted to, write instead this. Right? Isn't B equal to this?
Yeah.
So didn't I write 1? This is exactly what 1 says.
Oh, so I don't.
It's just I put this instead of B. Right?
Yeah.
So in English, it's sort of like somebody having a nickname. So if somebody has a nickname Tiny, instead of saying Fred, I can say Tiny. So B is also known as this. So wherever I see B, I can write his other name. I can write this.
It's like using substitution.
It is using substitution. That's exactly what it is. And you can see why I would call it that, because I've substituted B's other name in for what B is right there. Cool. So to solve this, you put your C's together. Add the 676 over. I think you guys can finish that out, right? Big numbers, but you don't care. It's not too bad. So at the end you get, oh, when you add this over?
Yeah.
Okay. And so C is 6137. And then B has to be C minus 676. So B would be this minus 676, which is something, whatever you said. 5461. I'll trust you guys. Don't get lost in the numbers. Numbers are semi-large, but it's not that bad. So this means, what exactly does this mean?
That there were 6,137 showings, performances of chorus lines.
I love it.
5,461
Of the
Beauty and
Beauty and the
the
Beast. I love it.
I got the same answer, but I did.
How did you do it?
I did C plus B was 11,598, and then C minus B was 676.
I love it. And then you did like elimination?
Right.
Beautiful. I love it.
Oh.
Not a damn thing wrong with that at all. Because like I said, there's a couple different ways to look at this. And depending on the way you set it up, you could want to do substitution or elimination. They got to come out to the same answer because they're really the same equations, right? You just kind of wrote it in a different order. So you got to get the same answer, yeah. Cool. All right, sweet. We're working on it. Any other questions on homework?
That's as far as I got.
All right, it's not bad. It's not a bad place to be in. Somebody started 4.5 yet?
Negative.
Have you looked at 4.5 yet?
Negative.
I want to review 4.5.
If you were able to do 3.5, 4.5 is easy. Because like I said, 4.5 is just 2 problems from 3.5 at once. Right? So let's do 1 problem from 4.5, and then we're going to get into chapter 5.
Holy crap, yeah, we are.
Yeah, we are.
Anyway, Joe, this is a small chapter.
All right. So, of course, what's the first step here when I want to try to graph the solution to this?
You need y-intercept.
Get y by itself.
Y by itself. Yeah.
So then everything falls into place, right?
Correct.
There really is nothing wrong with getting intercepts, but very often intercepts will be ugly. Like here, the x-intercept would be kind of ugly. And I need you to get the practice of getting it y equals something and then knowing what the slope and the y-intercept is. You have to kind of know how to do that pretty quickly. So that's why I suggest you go ahead and solve each one of these for y. Go ahead and do that for me. Let me know what you, oop, not equal. Let me know what you did in that. Here, I'll do the second one. Yeah. First is not too bad, right? Gotta be careful about dividing by negative if you do it that way. Good, right? So we've got that number 1. Solve for y. What'd you get?
Y is greater than 1/2 x minus 4.
Sweet. All right. That's what you should get. So you should get y. You subtract the x. Divide by -2. So the sign flips. The negative on the x becomes a positive, and 8 divided by -2 is -4. So that's what you should get there. Now, you graph the first one total. You graph the line, you make it dotted or solid, and you shade. And then on top of that, you graph the other one. So that's what I meant by it's just 2 section 3-5 problems at once. So how do I graph the first one?
Go to the y-intercept, -4.
Good. So -4, and then the slope tells me to go.
Up 1, to the right 2.
Good. What kind of line will it be? Dotted. Now, how do you determine which way to shade?
Find a point 0, 0, plug
Good.
them in for x and
So
y.
is 0, 0 is 0 less than 8.
Yes.
So then I would shade in the direction of 0, 0 because it worked.
Correct.
Right? Or some of you guys realize greater than is up.
Yeah.
I love it. As long as it's not too tilted, that's always pretty much easy way to go. So there's that one, totally done. Now on top of that, come in with 2. So what do we know about the second inequality? The y-intercept is
Oh, it's 3.
3, so I got to start there.
Yep.
And the slope tells me to go down 5. 1, 2, 3, 4, 5. Over 1. What kind of line will it be?
Solid.
Solid. I like straight. Solid. I decided not to do it straight. But oh well, too bad. And then you can decide which way to shade the same way if you want. If you plug 0, 0, is 0 less than or equal to 3? Yes, so you shade in the direction of 0, 0 because it worked. Here's a good example of it's less than, I want to shade down, but it's a little weird. Down is a little bit weird here, but it's tilted. That's still down from it in this direction. But the test point is always exact. So where's my answer? Where's my true answer?
It's everywhere that's darkish.
No, it's where the dotted and straight.
It's where the 2 shadings overlap, right? So right in this, here's my one line, here's the other line, so it's right in here. So on your homework or on a test, go ahead and make that section a little bit darker. Go ahead and shade it in a little bit more, okay? Some people like to, some people don't like to do what I do. They just put a little arrow in one direction, an arrow in the other direction, and then they come in, so they don't have all this crap all over the place. Whatever way makes most sense. If you guys want to use color pencils, I love it. I love my anal retentive students because it makes it so easy to grade. But if you don't want to, that's fine. I wouldn't either. So
everything in that shade area, you plug a point in
good.
that area.
So this point there, what's going to be true about that point? It works in both of these. This point there
No,
doesn't work in either one. And of course, in these sections, it only works in one of them. I like it. All right, cool. And in the real world, this is kind of used in situations where I have restrictions. Like you can have up to this many people in the elevator, and you can only have this many kids in there, or else it gets crazy. So you kind of see where's your safe place to be. Or when you're building buildings, you can only put this much load on this, and you can only have this much leaning on this, and you can only have this much wind, and you see where's your safe place to be. That's the place where this is used most often in real life, is restrictions, to see where can I be and be safe. Okay.
5?
So the nice thing with chapter 5, if you really don't like graphing,
I hate graphing.
there's no graphing in chapter 5.
I love it.
So we're kind of building up to chapter 6, which is factoring, which is really almost the most important thing. Because anybody here in business, going into business or something possibly? Do you know if you have to take eventually business calculus maybe? The thing that kills people in business calculus is the algebra. Because the first 2 steps of a problem are calculus, readship for calculus. The last 5 steps are algebra. So my students are normally able to do the first 2 steps is easy. This is brand new. And then the algebra, they suck at. So if you know how to factor pretty well and solve equations, business calculus is actually really easy. It's the factoring and the solving that kills people, believe it or not. So chapter 5 is not quite to factoring yet. It's kind of building up to it. It's the opposite. It's multiplying things out. Factoring is all about breaking it back up, right? So the very first thing we got to do is talk about the basics of multiplying, which involves this. Let me kind of build up to it. I know I just said multiply, but how do I write that? What's a better way to write that?
4x.
4x, right? Because I'm adding that. So somebody at some point in history decided to put a 4 there, and he told everybody what that meant. The funny thing is, it didn't have to be there. It could have been anywhere. But they put it there and said, that means I'm adding that many times, and now when we see it, we know what it means. So now they didn't have to write all this crap out. They could just write 4x. And then 80x, thank God they figured out how to do that, so they don't have to write freaking 80x's. Right? So then somebody else on the other side of the world had this, and he got tired of writing that all the time. And he's like, that freaking dude over there already took the 4 in front. He stole that. Shit. So let me put it in there. No, that looks like division. Maybe I can put it there. No, it looks like a freaking hat. That looks weird. So I'll put it there. And that's it. I mean, that's where all the properties of exponents come from. And we know these properties of exponents are really easy to get confused when you add, when you multiply, when you do all that stuff. But it really, all of them come from the basic definition. It's because somebody somewhere was lazy. They said, I don't want to write that. Let me just say 4 there. That means 4 x's. Can somebody tell me, is there really a 4 somewhere in here? No. That just means there are 4 of these. That's going to become very important later.
What is this multiplying? What is this multiplying?
Exactly. 4x is multiplying, whereas this coefficient, of course, means 4x is added. So it's just a way to condense it, a way to say it quicker. So, of course, the first property of exponents then, so we're going to go through all of them right here, right now. Make sure I go in the same direction. Yeah, okay, good. What would this be? Yeah, and why?
You add the
How long would the chain be? Well, I got 4 links here, right? Times 2 more gives me 6 total in a row, right? Of course, the most common mistake I see there is people say 8 because there's no like, well, you're multiplying, Jeff. 4 times 2 is 8. I'm like, I know what 4 times 2 is 8. It's not what it says. 4 x's in a row times 2 more x's in a row give you 6 x's in a row. Cool. How we doing? That's why exponents are not numbers. They don't act like numbers. They are just telling me how many of these I've got. So if I got 4 here, and then 2 more, of course I got 6 now, right? So what happens when I divide? Yeah, because here you got 6 of these up here, and 4 down here. So how many cancel? Looks like 4 cancel, leaving you with 2. Never do this, please, dear God. That's the whole reason we invented exponents, is so we didn't have to do this, but this is the reasoning. 4 cancel, leaving you with 2. Don't put x to the 3 over 2. Do you see where that came from? Somebody reduced 6 over 4. It doesn't say 6 over 4 anywhere in here. It says 6 x's over 4 x's leaves you with 2 x's. 4 of them cancel. How we doing? Is that cool? Okay. So what would it be if I raise something with power to another power? So let's say, like like that.
6.
That's when, yeah, that's when you multiply.
Beautiful. Because 3 groups of 2 x's. That's the definition of multiplication, right? You got 3 people all holding 2 apples when you got 6 apples altogether, don't you? Because this would be x squared times x squared, x times x squared, right? 3 of these multiplied. 2, 4, 6. Cool. All right, not too bad there, right? Let me see, I might be getting ahead of myself. Do this. Oh, I'm going to do it anyway. What would a negative power mean? Actually, before we get there, what would a 0 power mean?
0.
No, let's figure it out. If I put x cubed here, what do I have to put on the bottom to make it x to the 0, considering this rule here? Careful.
X cubed.
3.
Right? Another 3, right? Because what's the rule? When you divide, you subtract. How we doing?
Good.
6 minus 4 is 2, right? When you divide, you subtract. Why? Because you're dividing and they're canceling away. You're subtracting that many x's away. So what would I have to put on the bottom? I have to put 3. So the overall 3 minus 3 is 0. But what is something divided by itself? All right, so anything to the 0 power is 1. Let's investigate. Let's figure out why this is true. That's what that says. I can't get away with that, from that. We just proved that that's true by looking at the same thing in 2 different ways. What's the only thing I can multiply by and something stays the same?
1.
1. So if there's anything I multiply by and it ends up staying the same, the thing I multiply by, that thing must have been 1. So, for example, what is x to the 0 times x to the 7th? What's the rule?
7.
You add them, right? What's 0 plus 7?
7.
7. Careful now. 0 plus 7 is 7. And what did we just say? What's the only thing I can multiply by and the thing stays the same? 1. That must be 1 then. It's not 0. If x to the 0 was 0, I should have ended up with 0. I didn't. So this must be 1. This makes the most sense. How to get a 0 power? You have the same exponent, so they cancel. But what's something divided by itself? 1. I love it. Okay. Maybe.
X in general is always just 1. That's how I see it.
Not really. X could be anything.
Well, yeah, but I mean, like, if it's just x by itself, like x. And, I don't know,
But it's the same reasoning as when you do this. This is not 0, right?
No, that's,
When you divide these, do you have any x's left?
1.
Do you have any x's left when you do that? Any x's left?
No.
Are there any x's left when you divide those?
No.
No. Isn't that exactly what that says? No x's. But what do you get when you have no x's? You don't get 0. You get 1. So when there's no x's, what do you get? 1. They all canceled away. How are we doing? That's why a 0 power makes it 1. Okay. Because if I have none of them, I must have a 1. They must have all canceled away. Yeah.
So if you were to write x instead of 1, would you be wrong?
Yes. Because if you write this, what power is understood to be here? So how could 0x is equal 1x? Good. Because people get confused. When they hear me say 1, they think an exponent of 1. No, I mean x to 0 is 1. Not x to the first power. Just 1. Cool. So let's do a couple examples more of that here. Because I do a little bit more with this in the homework. So what's this here? I love it. Gotta love that. What did we just say? Anything to the 0 power is 1. Now to be totally honest, 0 to the 0 power is freaky. It's what's called indeterminate. And that's all I'm going to say about that. Whenever I have x to the 0, we're assuming x is not 0 itself. Because that is freaky. It's even worse than undefined. We have a whole new word for it, indeterminate. So let's just leave that one alone. You doing all right? Huh? Hell no. That's calculus level stuff. So don't worry.
Indeterminate?
Indeterminate, yeah.
That means they have no answer.
Exactly.
But there is an answer.
that's the weirdest thing.
But they can't find it.
Well, it involves, you have to know a little bit more about what each piece means. So that's why it's higher level stuff. Yeah.
That's 8.
What about this here?
8.
8.
I love it. The most common mistake I see here is somebody says it equals 1, but what's the only thing being raised to a 0 power? So this is 1, and 8 times 1 is 8. You guys see that?
Yep.
As opposed to what's this?
That's 1.
All one.
Yeah, because anything to the 0 power is 1. Because we're assuming it's not 0, so I'm never going to say anything about 0 in there again. That's it for that. So anything to the 0 power for us is 1. Cool. How are we doing? Good? Okay. Sort of good? Not really?
Yeah, why the last one?
Well, now we can look at it two different ways. What's being raised to the 0 power?
8 and the x.
8 is being raised to the 0 power? And? And what's 8 to the 0?
1.
1. What's x to the 0?
1.
You get 1. So now watch this. There. What's that?
1.
Okay. Right? To the 0 power, 1. Who cares what the hell that is? Anything to the 0 power is 1.
Dude, that'd be super.
We are going to see this kind of thing later. So it's
Make a little problems like that on the test.
no, I can make a 1 problem test, but I'm not going to do that.
To 0 power, yeah.
Yeah, that would be evil. Let me see. Oh, well, okay. Coming back to my properties. All right, guys. Can someone tell me? I like this proof because you kind of force it to be a 0 power, and you can kind of investigate what that means. So if I want to investigate what a negative power means,
Where's that properties of what?
properties continue.
Oh, okay.
Sorry, properties of exponents. What would I have to put on the bottom here to end up with a negative 1 power?
Negative
Careful.
3.
3. Because
Oh.
2 minus 3 is negative 1. So the bottom's got to be 1 bigger, right? Is that cool by itself?
Isn't it when you put a negative exponent, you put a one?
Yes, well, we're going to prove that right now. But what is this otherwise known as? You have x times x over x times x times x, right? How many x's cancel?
2.
How many are left?
1.
Where?
On the bottom.
So that's 1 over x. So a negative power means reciprocate or flip.
Wait, what?
So,
I get how you got negative 1x with that last part.
all right. 2 minus 3 is negative 1. That's cool. Now look at this a different way. Everybody with me? I looked at it one way using a property from earlier. I subtract the exponents when I divide. Now look at it a different way. Look at it directly. X squared is x times x. X cubed is x times x times x. How many x's cancel? How many are left? 1 on the bottom. And let's see, why does this make sense? What's the only way?
Why is there 1 on the top?
Because when I divide x by x, what do I get?
0.
1.
Oh, 1. Yeah.
X divided by x is 1. There's a 1 left on the top, right? For example, 3/9, what does that reduce to?
1/3.
Where'd that 1 come from? Same place that 1 came from, right? This is 3 over 3 times 3. 3 divided by 3 is 1. Same thing. X divided by x is 1. That's where that 1 came from. We're good? There's always an understood 1 up there anyway. It's just kind of hanging out. So, let me ask you this. A negative power then somehow means division. Do you guys see that?
Yes.
Because it's dividing by x. When I divide, if I have like x to the 8th, investigate. I don't know what else to call this. If I have x to the 8th, to make that number smaller, don't I have to put something underneath?
Yeah.
So to make it become 7, what would have to go down here?
X to 1.
Right? How are we doing so far?
Good.
Another way to make it become 7 is to put what right next to it. Because what do you do with the powers when they're right next to each other? You add them, so it would be x to the negative 1. So what did we just show? 1 over x to the first must be the same thing as x to the negative 1. When I divide, don't the powers go down? Because I'm losing x's, so they go down. When I add a negative power, doesn't that make it go down?
Yeah.
8 minus 1 went down to 7, right? No, I know what you mean. It would flip. I know, I got you. But when I add a negative power, it makes the exponent go down. The same way. That's why it makes sense that negative powers mean division in a way. Right? A negative power means flip. So to show you some more advanced examples of that, not too advanced, let's see. What would that be?
That'd be X.
I mean, X.
Why?
Because
If
you
you
need to take
make it first, it will be X power 1.
the reciprocal of the X.
Stay.
It's on the bottom side of the top.
Exactly. So better than writing it, now if you write it like this, that's where it gets weird. That's why I like the definition of flip. Wherever it is, it wants to be in the other place. It don't like it down there, it's negative. So you put it up top. So it flips from the bottom to the top.
So it's just like saying funny.
So if it was up top, what did it do? Went down. Right? This 1x was on the top, it didn't like it up there, did it? So what does it do? It goes down, it flips down. If it's on the bottom, what does it do? If it's a negative power, it flips up. So that's why a negative power means flip, period. Wherever it is, it wants to be on the other side. Right? So for example, if I have a to the negative 2 over b to the negative 3.
Wait, the answer is X?
Yes, the answer here is x.
You just completely flip it
So what do these two a's want to do?
to the bottom.
Go to the bottom. What do these three b's want to do?
And what?
So what do you think it is at the end?
So
B
B power
here,
3 over A power.
I love it. Do you see how these just flipped down? Those just flipped up. Negative power means flip.
Just with the negative, right?
Negative power means flip.
Always.
Always. A negative power means flip. What I get is people telling me that this is this. Now that is neat. This is not true, is it? Negative 2 is not equal to 1/2. Are we cool with that being totally crazy?
Yeah.
Right? A negative number can't. If I owe you $2, can I go, no, you owe me 50 cents? Ha, ha. I wish. Be careful. Nothing in math changes. This is new. A negative power means flip, not a negative number. A negative number is a freaking negative number. It just sits there. A negative power tells me to flip it. So those two A's didn't like it up there. They went down. Those three B's didn't like it out there, so they went up. Yes?
So always we have like two negative powers. There's one we have that.
You mean something like A, negative 2, negative 1? Like that? That one's nice because what do you do with these?
Well, those are,
You add them.
You multiply
Yeah.
them, careful.
oh,
Right.
oh, that's right, yeah.
When you raise a power to a power, you multiply. So that would be A.
Squared.
And let's look at this a different way, just a little different. Never, hopefully you would never do this. What does that inside mean by itself?
Flip it.
It makes it 1 over A squared, right?
Yeah.
Now what's that negative 1 in the outside mean?
It's got to flip.
Flip this whole thing back. So it ends up coming back to A squared. So this makes those two A's flip. And what's this negative power mean? It says take this and flip it, because that's what a negative power means. So yeah, the two negatives cancel. It's sort of like me saying, okay, turn around, Jeff. Now turn around again. I'm facing the damn way that I was in the first place, am I not? So it says flip yourself, and this says flip yourself again. So he says, well, I'm back right up on the top. Leave me alone.
So,
Right?
yeah, because two negatives cancel out, but what if there's only one negative that doesn't cancel?
Then it doesn't cancel out, yeah.
It's still negative, right?
Still negative.
But it still goes up.
But it still goes to the other place. It still flips. So it's still a problem like that. So if I had to do that problem, don't overthink it. There are two exponents on there. Let me do a property that will make it just one. What do I do when I raise something to a power?
Multiply it.
I multiply the two powers, right?
Yeah. Right.
So I get x to the,
Negative 6.
and what does that say to do?
Flip.
Flip what?
1 over 6.
Flip those 6x's down. There you go. 1 over x to the 6th. Yes.
What's just that one? I didn't get it.
Where are we at?
Yeah, this one.
This one?
Yeah, this is
So to do it directly would be negative 2 times negative 1 is 2, right? That's the way I would do it.
Yeah.
But just to look at it a different way, if I flip the two a's inside, because it's to a negative power, right? And then the negative power on the outside says flip again, well then it still ends up at a squared. Because how many times does it say to flip? Once, twice. Right, there's two negative powers. But then I can go more directly. I can say don't flip it all. Just say I don't have to flip it all, because I would just end up right back where I was. The two negatives cancel.
So we can do it that way.
Yes, please do. Don't do it this way.
Yeah.
I wanted to do it that way, but then I wanted to show kind of like a different way to look at it. But don't do it that way. Because what's the property when I raise something with a power to a power? What do I do with the powers? I multiply them, right? So hell yeah, I'm going to do that. If it ends up negative after I do that, I flip it. Okay, so normally, well, I gotta be careful. Don't want to make too many generalizations here, so. Let me think. I think there's one last sort of property to talk about. Say again? Not really, no. I can't remember what number property I'm on, but.
Number 6.
6?
6. Six.
We'll do 6.
Property number 5 was the x to the second power divided by x to the third power equals x to the negative 1.
Shoot! What do you think I do here?
You distribute the power
I love
to
it.
both.
So, tell me, exponents are based on what operation?
Distribution.
Exponents
Oh.
are based on what operation? What's 3
Pentagon.
cubed?
3 times 3
Multiplication. Exponents are based on multiplication. They play well with other multiplication then. It should be easy. It gets hard. This is what's coming up later. Why is that one more difficult? Because exponents don't play well with addition. They're not based on addition, they're based on multiplication. That's why I got to do this weird FOIL thing. Remember that? That's very close to in our future, right? That's why that's more complicated. This should be easy because exponents like multiplication. And that's exactly what's going on inside, right? And watch this. What is a coefficient based on? What is 3x actually? Don't tell me 3 times x. It's 3x is doing what?
Adding.
So coefficients are based on addition. So is this difficult to do here?
No.
No, because I just distribute, right?
Yeah.
Look up here. Exponents are based on multiplication. So is this difficult to do?
No.
No. I just distribute. I'm cubing a squared, so that's a to the 6. I'm cubing b negative 3, so that's b to the
Negative 9.
negative 9. And what's the last step?
You gotta put the b in the bar.
Right? It's sort of like reducing a fraction. You can't end with negative powers. If ending to a negative power, you put it on the other side. So what wants to go down?
B is the 9.
So the a's stay up, right?
Yep.
So this guy wants to go down because he's negative power. The a6 stays up there. The b9 goes down there.
So you don't do like A6 and then 1 over B9.
No, you could put it all together. Because that is what a6 times 1 over b9 would be, isn't it?
Yeah.
You just be a6 over b9. So don't do that. You can just go straight to put that underneath that guy. Bam.
I thought you timed when you have the parentheses.
You do multiply. 3 times 2 is 6. 3 times 3 is 9.
Oh, it looked like a 0.
Now I'm just
Sorry.
cleaning it up. Now I'm just flipping the 9b's, right? Because it's to a negative power. Okay. Maybe. And that's why, again, just to kind of go with this, that's easy, right? That's just 3x plus 6. What would this mean? Who remembers what that would mean? I'd have to write this thing 3 times and then FOIL it all. Oh, crap. This is hard because these don't like these. This is easy because these like these. Coefficients are based on addition. That's easy. Exponents are not based on addition. That's hard. Right? You see that all the time in math.
So,
This is to the 3rd power, so you'd actually have to do this. I'm getting a little ahead of myself, but some of you guys might remember. FOIL, FOIL, good God.
First out.
if the 2 is a negative, second is positive, does A go on the bottom?
Exactly. Whatever's to a negative power, you flip it. If it's on the bottom, it goes up. If it's on the top, it goes down. So let me show you this example here. Let me see what you guys think about this. Can you guys rewrite that with no negative powers?
Yes.
Do it.
On my pencil.
Can we?
So that was my first question. Can you? And then, even if you say no, I still want you to try. No, I cannot. Let me start working.
Wait, I have a question.
Mm-hmm. Let me ask you this, just to make sure everybody's on the right track. Which ones are you going to leave where they are?
Positive.
So be more specific.
Y
Which
third.
ones? Y third is going to stay, and A2 is going to stay. Everything else is going to move, isn't it?
Yeah.
So that Y cubed is staying. Why? Because it's a positive power. It doesn't want to go anywhere. And the A squared is staying.
Yep.
But those 4 B's are going to do what?
Go up.
Go up. And those 5 C's are going to
Go up.
go up. What's going to happen with these guys?
It's gonna go down.
Going to go down. He's going to go down.
Get down.
He's going to go down. Yes. Yeah. Okay.
I was just wondering if it's important if all the numbers, like, can they be in different positions as long as they're like,
Yeah, because it's just commutativity and multiplication.
okay.
Normally you put it in alphabetical order, but who
Okay.
cares?
I was going to ask the same question. Did
Oh,
you
okay.
add the X one first?
Yeah, I had it alphabetical
the
here, but I went out of it there, but I don't care.
Okay, it doesn't
I just want to make sure that these guys were in the same
Okay, because
place
they're-
and everything else was moving.
Okay.
Yeah. Do you guys see how that works? So when you get more complicated problems like this, your first step is just find everything with a negative power and move it. The first step is easy. You just move the damn thing. And then you come back in. I purposely made it so that I couldn't do anything else after that because I just wanted to focus on that one idea.
So there's like nothing.
Because is there anything you can do now?
No.
You can only combine them if the bases are the same, right?
Right.
There's no Y's, there's no C's, there's no B's, so nobody has something to go with. Aw. So this is it.
So you can just build on without doing any math. and just like, hey,
We did math. We
I know,
applied
I
the
mean,
negative power
Like
problem.
usually when you do that, if you do an equation, you gotta subtract x, subtract x.
Oh, no equation here though, right? It's just a simplification problem. And it's really sort of like me saying, you know, simplify this. If I said simplify that, what would you say? Yeah, I already simplified. This I could actually do at least one thing. And then I can't do anything else, so that's it. Okay. All right. So let me try a couple of things that confuse people, just to get them out of the way here. This is a very evil problem, believe it or not. What to the 10th? I like it. I'm not hearing any 9s. This is good. The most common mistake is for somebody to say this. And where does somebody get that from? And exponents mean I'm not multiplying yet. Exponents keep track of how many 3's I have to multiply. I got 2 3's here, 8 3's there, and what I normally write there is, I didn't see any freaking 9's. How do you have 10 of them now? Do you see that?
What if it's
So don't make that mistake. I have 2 3's, 8 times 8 more 3's is 10 3's. 3
What
to
if
the
it's a
10.
different number? Like
If it's a different base, what can you do?
thing times.
If you have 3 squared times 4 cubed,
You times the base?
No, you just.
you'd have the same, and again, this would be a mistake, the same mistake if you said 12 to the 5th. How do you have 5 12s when I only had 3 4's and 2 3's? How do you get 5 12s out of that? Doesn't make any sense. But can you use the property I did up here?
No.
Why? Because the bases are not the same. So what do you have to do then? 3 squared is 9.
64 times.
4 cubed is 64. And then you got to multiply those. Right?
That's so weird.
586. 576. Okay. something else. Oh, what about this here?
We're gonna multiply the square, then we distribute the 4 with the xy. You put the whole number with the xy. 4x to 4, y to 6.
And that's it.
You don't distribute the 4 to that.
There's no distribution of the 4 to go because there's no addition in there. Distributive property is multiplying over an addition sign.
Would it be wrong to put 4x plus 4y, and 4x plus 4y distribute both x and y?
Yes. 2 problems. Number 1, there's no plus sign in there. It's only multiplication, right? So it's really the same thing as 2 times 3 times 4. We had this problem before. Is this equal to 6 times 8? What was the mistake somebody made? They gave the 2 to the 3 and the 4. There's only one 2. There's only one 4 here. There it is. Distribution would be if I had this. Then I distribute. Because if I have 4x squared plus y cubes, there's 4 of them, right? That means I have 4 of each piece. You can see that?
Wait, isn't it 4x and 4y? Did you just say that?
I just said it's not that, yes. Look at this. What's x squared, y cubed squared? How do you do that? Don't you distribute the 2? Is that cool?
Yeah.
So there's a x4 and a y6. And what's sitting in front of it? 4. Okay, there you go. Right? There's a 4 in front of it.
So if you had an exponent on this problem distributed, would you still distribute the 2 on the
At the end, if there's a power out here, you do the FOIL that first and then bring the 4 through. Yeah.
So that's the answer.
But that's coming later.
So that's the answer.
That's the answer. That's it. That is it. So the problem you guys are having is it's been drilled in your head so much because when you solve equations, what's the first thing you do? Distribute. But have you noticed it's always been across a plus or a minus? Always. Because that's the only thing you distribute across with the coefficient.
So if it's x squared plus y, then
Exactly. If it was like that, then you would distribute because you got 4 of these and 4 of these. Whereas what's this say? I got 4 of these. Okay, I got 4 of those. Big deal. There it is. I got no other pieces to have 4 of, right? No other plus or minus. No other pieces to have 4 of. Okay, cool.
Oh, okay.
My favorite sound. I
The
like
light bulb came on, you know? Took me a little while.
All right. Good. Because when we start talking about, and this is in our near future also, polynomials, which are collections of these. They have several parts. So that's where I have to distribute when they have several parts. I got 1 part here. No distribution. Here I got 2 parts. Oh, I got to distribute. Parts distributed by plus or minus, separated by those.
So, for the that first part right there, example 3, if you put a plus sign between the x squared and the y cubed, oh, never mind, just, oh my god.
someone asked and then I asked.
I like that. I like that. Yeah, if I did that, yeah. I love it.
I wasn't here, okay?
All right. Mentally, he was somewhere else. Sure. Yeah.
No, but I mean, like, if you kept the power on the outside, though, just there you keep the power.
Say again.
How you square
Oh, but
those?
we have a 2 out here still?
Yeah, but I put 2 out there.
If I had that, I'd have to FOIL first
Foil first?
and then distribute the 4.
Okay.
Because what's order operation? So I multiply or exponent.
Exponent.
Exponent first,
Okay.
and then multiply.
Okay.
So that would be something
Totally different.
Yeah.
Okay. All right.
All right, here's probably the ugliest problem in section 5.2, or section 5.1, sorry. Something like this here. Yeah.
Are you stuck in 5.1?
And really, it's not that bad. What will save your ass more often than you realize is order of operations, like it just did a minute ago.
You can kind of do that. You can do that. You can do that problem in your head, right?
You could do several of these in your head, depending on how well you are with keeping track of what's going on. For me, though, as a teacher, I've got to grade something. So give me something to look at.
You want to do the exponents first?
I love it, right? Order operations. Saves your ass. Do not say 6. No, you got to do the power first, right? So how do you do the power, the cube of this?
Okay.
9.
Careful.
18.
What's 3 times 3 times 3?
Oh, 27.
3 3s. 27. A to the
12.
12, right? So that's right there. I want to stop right for a second. Exponents you multiply here, right?
Correct.
Because you are cubing A4, which means A4, A4, A4. There would be 12 A's then, right? This is a number, not an exponent. So people get confused. They do 3 times 3 because they're thinking, well, 4 times 3, why would I do 3 times 3? Because that's an exponent, that's a number. I want to make that distinction right now. This is not a 4. This means 4 A's. So when I cube 4 A's, I get 4 A's, 4 A's, 4 A's, 12 A's. There it is, right? 12 A's. But when I cube 3, that's 3 times 3 times 3. Very basic. So numbers will never act the same as exponents because they're not the same damn thing. Of course, because that's an exponent, not a number, right? That's an exponent. I don't want to freak you guys out. That is the number 4. Is everybody cool with that? That is the number 4. I understand. But that means 4 A's. It doesn't mean a 4 is in there. It means I have 4 A's in there. If I have 3 groups of 4 A's, I have 12 A's.
You gotta distribute to every single bit of it.
Exactly.
You can't just.
So another way to look at this real quick is what power is the 3 to understood to be?
3.
3 is to the what power?
Cube. Third power.
Right here.
3. Wait, what?
Right here is to the what power?
1.
Understood to be to the first power, right? I haven't put that in yet. So right there is to a first power. What do I do with powers here? I multiply, don't I? So if you write it with an exponent, then it will act the same. So this is 3 to the 1 times 3, 3 cubed. Which of course is 27. With me? And now you keep going. You multiply the exponents.
A12,
A12.
B6,
Good. B6.
4, A2, B6.
And this will be, yeah.
4.
Again, 2 squared. So that's 4. A,
2 second.
good, squared.
And B6.
B6. I love it.
And then
But you have to separate the AB.
Say again.
You have to separate the AB.
How do you mean separate?
Well, you gotta
And a foil.
You can add.
What's the only operation going on in here, really?
Distribute.
Multiplication. Right? How are we doing? Isn't this 27 times A12 times B6?
Yes.
Can't I multiply in whatever order I want to? So what order am I going to do it in? Number times number, because I can do that. A's times A's, because I can do that. Right? So don't overthink this. It really is just 27 times 4.
108.
Okay, 108. A12 times A squared.
8 to the 24th power.
Careful.
A4,
A14. I want you guys to realize that's such an easy mistake to make, especially if you just multiply them. You're like in that mode. There's 12 A's there. 2 more A's make 14. B to the 12. I love it.
You got me.
I don't mean to, but it's really easy to make that mistake.
Yeah.
Right? How you guys doing?
Good. Amazing.
That's the worst problem.
In that section, yes.
What number is that?
That's like number 77, 78 in section 5.1.
Went up that high?
Oh, yeah.
Right here. Yeah, we are. 5.
Now, in the interest of full disclosure, we actually already did section 5.2. Haha. That's the negative product, the negative power rules. Yeah.
How do you know that it's only cubing the B where it's 2AB cubed?
Oh, here? Oh, no, here.
Yeah.
Because an exponent, now guys, this is a good question. Because I see, way too often I see this becoming this somehow.